So, quick review of what we learned so far. The magnetic force on the moving charge is QV cross B. But we've already known what the electric force is. It's QE. So what if we have both things, both kind of fields, existing at the same time? Well, then the force is just the combination. QE, there it is, electric force, and the QV cross B force. So that's the magnetic force. So there we go, the entire force on the charge. And now let's define magnetic flux. I bet you're suspecting it's going to be similar to electric flux, and if so, you'd be right. Similar, at least. Now, north and south pole. Remember that the lines of magnetic field point in the direction of the north pole interaction of a compass, but they don't point in the direction of the magnetic force. So even though the compass needle lines up with these magnetic field lines, that doesn't mean that's the direction of force on the moving charge, which is what FB is talking about. FB is the force on a moving charge. That's not the direction that the compass needle points, okay? It's QV cross B. It's perpendicular to the VB plane. All right, so make sure you understand that. That's a very easy misconception to maintain. Let's take an area element. Here's surface dA. And here's our vector area element dA. Remember that? Here's our magnetic field, vector quantity piercing through this surface. Here's the parallel part, and we have the perpendicular part. Perpendicular to what? To the surface. So therefore it's in the same direction as dA, dA vector. So the magnetic flux through the surface, phi sub B. Magnetic flux through a closed surface, you're familiar with that term, that's cap phi sub B. So we'll differentiate those two symbols. Now, the perpendicular magnetic field is B cosine of theta. So B cosine of theta gives you the part that we're interested in to produce flux through dA. Magnetic flux, d phi sub B, is B perpendicular dA. That's B cosine of theta dA, which is B dot dA, the quantity of the magnetic field to the surface dA, just like we learned with electric flux. So the flux through the surface is integral of B dot dA. Flux through the surface. If the B field is uniform on the surface, then we can just summarize the magnetic flux as B perpendicular A, which is BA cosine of theta. Now, if the magnetic field is parallel to the vector dA, which is really perpendicular to the area itself, not considering the vector nature, then the magnetic flux is BA, right? And that's Tesla, magnetic field intensity, times meter squared, that's the units, Tesla meter squared, and that is the definition of magnetic flux, or Webers. So Weber is a Tesla meter squared. Now, just to deviate momentarily, which is really important, we have never discovered magnetic monopoles. No magnetic monopoles. Therefore, the total magnetic charge, if you will, you might not have heard that term before. There's reasons for it. Magnetic charge is not something that's, tossed around, because we don't know that there is such a thing. In fact, it's zero. So here's an analogy. The magnetic flux, total magnetic flux enclosed, closed integral of B dot dA, is equal to, instead of Q enclosed over epsilon 0, as with electric flux, we say magnetic charge enclosed over mu 0, the corresponding magnetic permeability corresponding to electric permittivity. We'll have a little more discussion on that later. So that whole thing is zero. In fact, it's always zero because there are no magnetic charges in isolation. So we have electric charges in isolation, like an electron or a proton or some other charge that's sitting there by itself, and our Gauss's law electric flux, closed integral of E dot dA, Q enclosed over epsilon 0, and that's a non-zero quantity. Now it's 0. So closed integral of B dot dA is equal to 0. This is Gauss's law for magnetism. And because it's 0, of course, that makes this whole result very simple, doesn't it? The B field lines are continuous. There's no beginning, no destination, no end, and therefore any magnetic field coming out of a surface ultimately goes back into the surface to continue or complete the closed magnetic loop. Now, since B perpendicular is the B field through a surface, it follows that the differential magnetic flux is B dot dA, which is this B dA perpendicular. So we can now define B as d phi sub B over dA perpendicular. And that is flux per area. So flux, total quantity of magnetism in an area, divided by the area, is a definition of magnetic field intensity. So B can be thought of as magnetic flux density because it's the density of the flux. How much flux per area? Think of the flux as total quantity of lines, if you will, of magnetism through an area. Through an area divided by the area, and it's the density of those flux lines. Hopefully that is intuitive. So magnetic flux density and B field intensity mean the same thing. It's Teslas. Now, do a quick example. We're going to have a B field, magnetic flux density, or the B field intensity, penetrating the surface. The surface is at 40 degrees compared to the B field, and the flux is 1.2 Webers going through that surface. We have 4 meters on a side for the area. So, magnetic flux, BA cosine of theta. And that's 1.2 Webers, as given. So, magnetic field, just do the algebra, flux over A cosine of theta. 1.2 over 4 squared, cosine of 40, gives us our small fraction of a Tesla. So we can convert that to Gauss, 980 Gauss.